Good morning, students. In the last class, we discussed capacitor and capacitance. So today we will discuss combination of capacitors. So capacitors be represented by two parallel lines, parallel straight lines. So this is the symbolic representation of a capacitor. So this one is fixed capacitance, right? So next, another one is same capacitor, two parallel lines with an arrow mark. So that one is variable capacitance, right? So now here we are going to discuss the combination of capacitors. So in the combination we have two types of combination. One is series combination and another one is parallel combination. So very important for 5 marks. They ask for the derivation, right? So first we will go on series combination. Capacitors are connected in series, right? So when we say that the capacitors are connected in series, right? So when two or more capacitors which are connected end to end, then those combination we call as series combination, right? So when we say that the capacitors which are connected in series means two or more capacitors which are connected end to end. That means one end of the capacitor is connected to the another end of the capacitor, right? So that one we call as series combination. So here one end of the first capacitor is connected to the second end of the second capacitor, and the second end of the second capacitor is connected to the third end of the capacitor, right? So this we call as a series combination, right? So when we apply the potential difference across the series combination, right? So when we apply the potential difference across the series combination, the charges will remain same on each capacitor, right? So this we call as capacitors connected in series, right? So when we say that capacitors are connected in series means two or more capacitors which are connected end to end, and when we apply the potential difference across the capacitors, then charges will remain same on each capacitor, right? So this gives what the capacitors which are connected in series, right? So now here we are going to derive the relation. So for consider two capacitors of capacitance C1 and C2, right? So capacitance C1 and C2, right? So initially we apply the voltage V. So voltage across the capacitance C1 is V1 and voltage across the capacitance C2 is V2, right? So here the charges will remain same on both the capacitors, right? So from the potential difference V is equals to, we can write V1 plus V2, right? From the definition of capacitance, C is equals to Q divided by V, right? So here we have V, so V can be written as Q divided by C. So the voltage across the capacitance C1, we can write this one as V1 and capacitance C1. So similarly, voltage across the capacitance C2, that is V2, is equals to Q divided by C2, right? So now substitute V1 and V2 in the equation 1, right? So potential V is equals to, so V1 we have Q by C1 plus Q by C2, right? So this one calling equation 2, right? So now compare this one with the equivalent capacitance, right? So equivalent capacitance means a capacitor having the capacitance which produces the same effect as the combination of capacitance. So that one we call as the equivalent capacitance. Right? So calling that one capacitance. So that is Cs and voltage across is V. So applied voltage is same for both the cases. Right? So what is equivalent capacitance means? A capacitor having capacitance which is equals, that means it produces the same effect as the capacitors which are connected in the combination. So that type of capacitance we call as the equivalent capacitance. So again, by the definition, so Cs is equals to Q divided by V, right? So calling this one as equation 3, right? Or we can write this one as V is equals to Q divided by Cs, calling this one as equation 3, right? From equation 2 and 3, right? So in the LHS we have the same potential. That means we applied the potential across the combination is same as that of the equivalent capacitance. So V is same for both the cases. So here LHS is also same. That means RHS we are equating Q divided by Cs, that is equals to Q by C1 plus Q by C2, right? So in LHS and RHS we have the common term Q, so we can cancel. So 1 by Cs is equals to 1 by C1 plus 1 by C2. So this gives the final expression when the capacitance which are connected in series. So Cs suffix represents what? The capacitance which are connected in series. So if we have more number of capacitors which are connected in series, right? So here C3, C4 and up to Cn. So if we have any n numbers of capacitors which are connected in series, so the formula is 1 by Cs is equals to 1 by C1 plus 1 by C2 plus 1 by C3 and so on up to 1 by Cn. If we have n capacitors which are connected in series, right? So now if all the capacitors have the same capacitance, right? So all the capacitors have the same capacitance means all the values are C, right? So we have connected n number, right? So now if all the capacitors has same capacitance, so directly we can write 1 by Cs, that is equals to n divided by C. So Cs is equals to C divided by n, right? So if two capacitors which connected in series having the same capacitance C, so we can directly relate Cs is equals to C divided by 3. So if we have four capacitors which are same capacitance, so we can directly relate Cs is equals to C divided by 4, where n is the number of capacitors connected in series. So n is the number of capacitors which are connected in series. So ನಮಗೆ 3 capacitors ನ ಕನೆಕ್ಟ್ ಮಾಡಿದ್ರೆ n value 3 ಇರುತ್ತೆ. 4 capacitors series ಅಲ್ಲಿ ಕನೆಕ್ಟ್ ಮಾಡಿದ್ರೆ n value 4 ಇರುತ್ತೆ, right? So this we can also write this one as Cs is equals to C1 C2 divided by C1 plus C2. Problem solve ಮಾಡಬೇಕಾದ್ರೆ ಡೈರೆಕ್ಟ್ ಆಗಿ ಇದನ್ನ ರಿಲೇಟ್ ಮಾಡ್ಕೋಬಹುದು. Cs is equals to C1 C2 by C1 plus C2. So this is for the n capacitors of individual capacitance C1 C2. That means different capacitance which are connected in series. So here all the capacitors are connected in series having the same capacitance. That means each capacitance value is C, right? So if any capacitance value is 10 microfarad, that means all the capacitance value is 10 microfarad, right? So then equivalent capacitance of the combination of this series becomes, so Cs is equals to 10 divided by, if I connected 4, so it becomes 10 divided by 4. So if I connected 2, so it becomes 10 by 2, right? So this is series combination, so very important for 5 marks derivation, or they ask for 3 marks, right? So here main, the charges on the each capacitor will remain same in the series combination, right? So here the potential divides, so applied potential is V, it divides potential V1 across C, that is C1, and across C2, that is V2, right? So this, if you know the relation, so we can easily derive. So next, capacitors which are connected in parallel. So when we say that the capacitors which are connected in parallel, so the same ends of the capacitor is connected to the another capacitor, right? So same end means, so this is the capacitor C1, the one end of the capacitor is connected to the same end of the another capacitor. So this combination we call as capacitors which are connected in parallel. Now if we apply the external potential across those capacitors, so this one is the potential V. So here charges are divided on the two capacitors. So taken C1 is the capacitance of the first capacitor and C2 is the capacitance of the second capacitor. So potential across those two capacitors will always remain same, right? So in parallel, potential is same across the combination, right? So charges are divided. So here charge Q1 and charge Q, right? So the total charge Q is equals to Q1 plus Q2. Calling this one as equation 1. So again, from definition, capacitance C is equals to Q divided by V. So we want the charge which are stored on the capacitor C1, right? So for that, Q1 is equals to C1 V. So potential is same, we taken V, right? So capacitance of the capacitor 1, we taken C1. Similarly, Q2 is equals to C2 V. So calling this one as equation 2. Substitute 2 in 1, right? So Q is equals to C1V plus C2V. So calling this one as equation 3. So again, by the equivalent capacitance, so equivalent capacitance means the capacitance of a capacitor which produces the same effect as the capacitors which are in combination, right? So that one we call as the equivalent capacitance. So that we taken here Cp, right? So again here Cp is equals to Q by V. So Q is equals to Cp into V. Calling that one as equation 4. right? So from equation 3 and 4, so charges on both the capacitors are same, so we can equate Cp V is equals to C1V plus C2V. So in all the terms V is common, so we can cancel. We get Cp is equals to C1 plus C2. So this gives the final expression. The capacitance which are connected in parallel. So if n capacitors which are connected in parallel, we can write Cp is equals to C1 plus C2 plus C3 plus and so on up to Cn, where n is the number of capacitors which are connected in parallel. Right? Now, if all the capacitors has same capacitance, right? So all the capacitors has same capacitance and Cp is equals to C plus up to N, right? So Cp we can write N into C, where N is the number of capacitors connected in parallel. So in the examination, it asks for derive the expression for the capacitors which are connected in parallel. So you can stop up to this. Cp is equals to C1 plus C2. So this is for the extra. While solving problems, we can use these relations, right? So this is about the combination of capacitors. One is connected in series and connected in parallel, right? So in examination, we need to write both the diagrams. One, the capacitors which are connected in parallel along with the equivalent capacitance, right? So equivalent capacitance Cp and its potential is V, right? So very important for 5 marks. If they ask for series or they ask for parallel. If they ask for the parallel, they will ask this for 3 marks, right? So on the last topic, energy stored in a capacitor. So very important for 3 marks. Several times they ask this one for 3 marks. Energy stored in a capacitor, right? So consider a parallel plate capacitor. So that means two conductors which are connected in parallel, right? So initially we taken two uncharged conductors, right? So initially the charge on each conductor is 0, right? So now shift the charge or bringing the charge from one conductor to another conductor. So I will call this one as conductor 1, this one as conductor 2, right? So bringing the charge from conductor 2 to the conductor 1. That means we are shifting one charge from conductor 2 to the conductor 1. So that means in conductor the maximum charge carriers are the electrons. So if we are shifting the electrons means the conductor 2 from we are shifting the electron from conductor 2 means it becomes negatively charged because it loses its electrons. So the conductor 1 gains the electrons, that means it becomes positively charged, right? So here we will discuss in step by step. So conductor 2 become minus q dash, right? So considering this situation, now if I shift a small charge from conductor 2 to the conductor 1, so that charge I will take as delta q dash. So I am shifting a small charge from conductor 2 to the 1, that means second plate to the first plate. So here the work is done. So that work is we call as delta W. That means small work is done by shifting a charge, that is delta Q dash, right? So the charges on the conductor one is Q1, Q dash, and charge on the second conductor is minus Q dash, right? So now the potential on the conductor one is V1 and conductor 2 is V2. So in the intermediate state, the potential difference between the two conductors, we taken that one as delta V dash, right? Or we take on that one as V dash is the potential when in the intermediate situation, right? So we need to find the total work done to bringing the charge from conductor 2 to conductor 1, right? So for that, first we need to find the work done for a small charge. Then we can find for the work done to the total charge, right? So we know V dash is equals to Q by C, where C is the capacitance of the capacitor, right? So capacitance of the capacitor is C, right? So now small work is done. So that one we written as delta W is equals to V into delta Q dash, right? So we are shifting the small charge from second plate to the first plate, hence it does a small work. So we need to find the total work done, right? So delta W is equals to, we know V, that is Q dash by C into delta Q dash, right? So this is the work done to bringing the charge, small charge from second conductor to first conductor, right? So for total work done, W is equals to integration of delta W. So if we integrate the small work done, so we get the total work done in total bringing the charge, right? So this gives what? The total stores on the charge, that one we taken as Q. So initially it is an uncharged conductor. So value starts from 0 to Q, right? So integrating from 0 to Q. Q is the total number of the charges which are stored in the capacitor, right? So W is equals to integration of 0 to Q. So we know dW, that is Q dash by C to delta Q dash, right? So C is constant, 1 by C taken outside, so 0 to Q, Q dash, delta Q dash, right? So we have the integration formula, that is x power n dx, we write that one as x power n plus 1 divided by n plus 1. So here in place of x we have q dash, so its power is 1, right? So that means q dash power 1 plus 1 divided by 1 plus 1, and substituting the limit 0 to q. So 1 plus 1 become 2, that is 1 divided by 2c. So in place of q dash we are substituting the limit, upper limit, that is q square minus 0, right? So work done is equals to q square divided by 2c. So this work done is stored as a potential energy. So that one is the electrostatic potential energy, right? So that is U, that is equals to W, right? So U is equals to Q square by 2C. So this gives the expression for the energy stored in the capacitor. It stores the charge Q and its capacitance is C, right? So the other forms of energy, so here we can write U is equals to relation we have 1 by 2C Q square, right? So we know C is equals to Q divided by V. So Q we can write CV, right? So substitute here U is equals to 1 by 2C in place of Q. So we can write CV whole square, right? So U is equals to 1 by 2C into C square V square. So C get cancels. So we get U is equals to 1 by 2 CV square, right? So this one is the other form in the form of capacitance and voltage. So here we have capacitance and charge, right? So next, again U is equals to, so by that relation 1 by 2 C. So in place of V we can write Q by C, right? So Q by C whole square. So U is equals to, sorry, it's the same relation, CV square. So C is equals to Q by V. Q by V into V square. So V get cancelled. U is equals to 1 by 2 Q into V. So these are the three forms of the energy which is stored in a parallel plate capacitor, right? So these will be helpful while solving the problem, right? So in the exam you can stop up to here. So U is equals to Q square by 2C. So very important for 3 marks. So on the last, energy density. So again by this relation we are going to find the energy density, that is electrostatic potential energy density, right? So again, so U is equals to Q square by 2C. So we know surface charge density on the conductor. So we have the relation sigma is equals to Q divided by A, where A is the area of the plate and Q is the number of charges which are stored on the capacitor, right? So this Q we can write Q is equals to sigma into A, right? So now we know the electric field intensity at the surface of a charged conductor. We know the relation E is equals to sigma by epsilon naught, right? So from this relation we can write sigma is equals to E into epsilon naught. So substitute the sigma value in this relation. So we get E epsilon naught A. So Q value becomes E epsilon naught A. Now substitute this Q value in the energy equation. So we get E epsilon naught A whole square by 2C. Right? So again we know the relation C is equals to Q divided by V. Right? So E square epsilon naught square A square divided by 2 into Q divided by relation. So capacitance C is equals to epsilon naught A divided by D. So this is for a parallel plate capacitor. So substitute 2 into epsilon naught A divided by D. So A get cancelled, epsilon naught get cancelled. So we get 1 by 2 epsilon naught E square A into D. Right? So where A is the area of the plate and D is the distance between the two parallel plate capacitors. Right? So D is the distance. So overall this we call that one as the volume. Right? So 1 by 2 epsilon naught E square into volume. Right? So here we have the energy U. So U divided by energy. So U divided by volume, that is equals to 1 by 2 epsilon naught E square. So we calling this ratio U by V, energy per volume. So that one we call as energy density. So we know the density is mass by volume. So here we have the energy per volume, we call that one as energy density. So energy density, that is equals to 1 by 2 epsilon naught E square. So this one is the relation in terms of electric field. That means the energy stored in a capacitor due to the electric field E, we have the relation 1 by 2 epsilon naught E square. Here we will write one more relation, that is C is equals to epsilon naught A by D. So by using these, we derive the energy density, right? So this is about the energy stored in a capacitor, right? So next, applications of capacitor or uses of capacitor. So capacitors are used for uses of capacitor. So it is used to store the charges. So from that relation, we can also say it is used to store the energy, right? So few more applications. It is used in filters. Also, it is used in oscillators. Right. So these are the few applications of capacitors. So this is about the energy stored in capacitors. So very important for 3 marks. So final relation, we have energy stored. U is equals to 3 relation. U is equals to Q square by 2C, that is equals to half CV square, that is equals to half Q into V. Right? These are the 3 forms of the energy storing capacitor, and energy density is 1 by 2 epsilon naught E square. Here we write volume, that is equals to area into distance between the plates. So A into D gives what? Volume. Right. So in the next class we will discuss problems related on the capacitor and capacitance. Right. Thank you.